Today we're going to dive into the fascinating world of imaginary numbers and explore their application in both programming and physics. Now, you might be wondering, what exactly are imaginary numbers? Well, sit tight and get ready to have your mind blown. In mathematics, an imaginary number is a complex number that can be written in the form a plus b, where a and b are real numbers, and I represents the imaginary unit, defined as the square root of -1. You may think, wait, how can you square root a negative number? That's not possible. And you're absolutely correct. That's precisely what makes imaginary numbers so intriguing. While imaginary numbers themselves do not exist in the physical world, they are incredibly useful in various scientific and engineering disciplines, including programming and physics. Let's start by exploring their role in programming, shall we? In programming, imaginary numbers find practical application in areas such as signal processing, electrical engineering, and computer graphics. For instance, in signal processing, complex numbers, including imaginary numbers, are used to represent and analyze digital signals. By utilizing the mathematical properties of complex numbers, engineers can manipulate and process signals more efficiently. In computer graphics, imaginary numbers come into play when dealing with transformation operations like rotations, scaling, and 3D graphics. Complex numbers can simplify the calculations involved in these transformations, making them more computationally efficient. Additionally, in certain algorithms like the fast Fourier transform, FFT, complex numbers are utilized to analyze and manipulate data efficiently. Moving on, let's talk about the role of imaginary numbers in physics. Believe it or not, they have a significant impact on our understanding of the natural world. One area where imaginary numbers find application is in the study of quantum mechanics. Quantum mechanics deals with the behavior of particles at the atomic and subatomic level, where things can get really weird. Imaginary numbers come into play through the Schrödinger equation, which is fundamental in quantum mechanics. This equation describes the time evolution of a quantum system and involves complex numbers to represent wave functions. These wave functions describe the probability distribution of finding a particle at a specific position and time. Moreover, imaginary numbers are employed in electrical engineering and electromagnetic theory. In alternating current, AC, circuits, where voltage and current vary sinusoidally, complex numbers, including imaginary components, are used to represent impedance. The concept of impedance allows engineers to analyze and design electrical circuits efficiently. It enables us to calculate quantities such as voltage, current, and power, considering both the magnitude and phase relationships of AC signals. In the field of optics, imaginary numbers are essential for understanding the behavior of light waves. For example, when light passes through a medium with different refractive indices, complex numbers are used to describe the phase shifts and the interaction of light with matter. By using complex numbers, physicists can accurately model and predict phenomena like refraction, diffraction, and interference. Let's not forget about the fascinating world of complex analysis. Imaginary numbers are the key players in this branch of mathematics, where they are used to solve complex equations and analyze functions. Complex analysis provides a powerful framework for understanding many phenomena in physics, such as fluid dynamics, heat conduction, and quantum field theory. To sum it up, imaginary numbers may seem like abstract mathematical concepts, but their applications extend far beyond the realm of pure mathematics. They are invaluable in programming, enabling engineers to process signals more efficiently and tackle complex calculations in computer graphics. In physics, imaginary numbers help us understand and explain natural phenomena at both the macroscopic and microscopic levels, such as wave behavior, quantum mechanics, and electrical engineering. So the next time someone tells you that imaginary numbers are just a figment of imagination, you can confidently tell them that they play an indispensable role in both programming and physics. Without them, our world would be missing some essential tools and knowledge that drive technological advancements and deepen our understanding of the universe. Isn't that just mind-blowing? Thanks for joining me on this incredible journey, and until next time, keep exploring the fascinating world of numbers.